Hi, good evening, everybody. Um, so I'm Chamara Jayalath from Moley Robotics. So at Moley, we are building a fully autonomous robotic kitchen. So the idea is we mimic the motions from chefs and try to cook any recipe as much as a human would. Um, and this is our robot, uh, what we have at the moment. Yeah. So the idea is to cook anything coming from a recipe. Yeah. So as you can see from here, and also in a lot of robotic applications, robotic arms are very crucial. So today, what I'm gonna be focusing on is how to build robotic applications with robotic arms. So robotic arms are basically a chain of mechanical links which are controlled by joints, which are actuated by the motors. So the question is, you have a robot which can move, and it has a degrees of freedom of the movement depending on the number of joints that you have. So the question is how you can do something useful or some task using this robotic arm. So today I'm gonna introduce you to toolkits uh, and go through a little bit of the code uh, to show you uh, how we can pick up object and place it on a different table, basically. Um, so let's go to the requirements for this. So the first thing is we need to model our robot, and then the environment, of course, and then we need to sense the environment itself, and then we need to, since it's a pick and place, we need to create the motions for the robot without any collisions in the environment. And then after, so from you can go from somewhere to the other place with the robot, and then you need to create the feasible trajectories that can be run on the actual hardware of the robot, depending on the velocities, acceleration, and the torque of the motors, basically. So to go a little bit deeper into these requirements, so how would you model your robot? So the main thing is you would get the robot configuration normally as a URDF file in the robotic community from the manufacturer of the robot, which defines the relationship between the joints of your robot. This gives you the geometrical representation of your robot, and also from the manufacturer you will get the dynamic configuration of the robots, like the velocities, the accelerations, the motor torque that it can go with. So the URDF itself will come as XML, and given this, you can basically model your robot. So given that you have these parameters, let's get this two-arm robot as an example here. So this is my robot. It has two joints to move, and given these joint angles, I can find the geometrically where my end effector is, which is this XY here. We call this forward kinematics in robotics. So given length of your links and the joint angles, you can find where your end effector of the robot is. And then the other question is, okay, I have my robot somewhere and I want to put it somewhere else in a different pose. Let's say X1, Y1. And then the inverse kinematics is to find the joint angles here to put your robot to that place. So given we can find this mathematical definition for the forward kinematics and the inverse kinematics, I can put my robot anywhere in the space, basically, where it can reach, obviously. So given that, the next thing is I have to move my robot from one place to the other, which means to go from here to there, I need to find continuous configurations of the robot without colliding as well with the environment. So this is called motion planning in the literature, and there are different algorithms to do this. And finding the correct algorithm for your application, of course, depends on the kind of application you do, as well as the environment you work in, as well as the capabilities of your robot. So given that you have a configuration, okay, I want to move from here to here, the robot, and I know how it would go from which joint angles to which joint angles. But still, you need to tell the robot how fast, with which acceleration, with which motor torques that it should go. We call this trajectory generation, so time parameterize your motion plan, and that gives you a robot configuration with respect to the time. So it's a function, the function with respect to the time, basically. So given this, I have my robotic motion as a function of the time. I can send these commands to the robot controller, the position, velocity, acceleration, or torque, depending on the API or the interface the hardware provides, and you can start to move your robot. So this is kind of the very uh, small introduction to the requirements that we need to have to develop such an application. And because of the complexity and everything, it's as developers, it's very important to find a robust toolkit to do this. So robotic operating system, in short, ROS, is one such framework. So it provides you with the tools to build your robotic application as a computational graph of nodes. And this node can communicate to each other using ROS messages. And you can see here a small example. So we have the ROS master, which registers all the nodes in your application, and it allows the nodes to know each other and communicate between each other using ROS services, topics, and actions. And the language-wise, ROS supports C++ and Python at the moment, and there is experiment version of Java. So the good thing about ROS nodes, so if as a Java developer, you develop a camera controller, for example, and I, as a C++ developer, develop some backend in the robot controller, let's say. But we can still communicate between each other using ROS messages, even though we are in different languages. So it's language agnostic, which is a very good thing in the development. So the next thing is a Moveit. Moveit is a toolkit which is built on ROS, which provides complex algorithms for kinematics, motion planning, trajectory planning, perception, and all these kind of necessary algorithms for robotic operations. So when as Moveit itself is a ROS node, you can communicate with Moveit using ROS commands or ROS messages, and can interact with your robot and also use the capabilities from Moveit to get, let's say, kinematics or the collisions of your environment. And then we have RViz, which is a 3D which is a toolkit used to visualize the robot model and your environment. As well, RViz allows you to develop UI plugins that you can load in the RViz and start to interact with the robot itself. So these are basically the main toolkits that we will be using to build the robotic application. And these toolkits are used by a lot of industry and a lot of research community, and there's a big support from a lot of people, and it's evolving really, really fast. So in our application, as we told, we have this move group where I'll be communicating with to get the robotic functionalities and use the robotic algorithms. And then we have the world model where we will update our environment with. And then I have the camera controller here, which is simulated right now, where I would get the current environment object poses, for example. And then the RViz node will be the UI interface to us to communicate with other nodes. And then let's say that I get a robotic configuration from some manufacturer, which defines me how my robot geometrically looks like, and also the other parameters like velocity, acceleration, limits. I can go to the Moveit setup assistant and load my robot there and start to configure this particular package in the way I want to control my robot, as well as which kind of algorithms and which kind of plugins you want to use with Moveit in your application. So we load the robot here. It's easy. You load it, and you can also define the self-collision, which are allowed for the robot to happen. And then you can go ahead, and because your robot is somewhere and you want to link it to your environment, which is your world coordinate system, let's say, and you can define it here. And then with these names, you can also access it in your code. And then as you can see here, our robot has a gripper here and as well this actual robot arm here. So I can define different groups here. So I define here from the base to the last joint here. So this is one move group that we use for all our planning and stuff. And then I can also use my gripper separately and configure it in the Moveit, and it will use as a separate group. Yeah. And as well, so this is done now. And I go ahead, let's say my robot is somewhere and I want to actually, after doing something, I want to put my robot in a default pose always. And I can do these sort of things here. I can move my robot and I can tell, okay, this is my default pose. And I can save that and I can use this in my code with the same names, which are done here. So you do all of these configurations here. And then I can export this package, which is a ROS package, to my file system that can be used to access all the robot related robot related capabilities. Yeah. So the next thing is given that we have our move group package to access the robotic functionality. Now let's go ahead and see how we can create actual robot application. So the first thing is to use Catkin and create our workspace. So I go here and I create my folder, pick and place project, make a source folder there where all my code will lie, and then do a Catkin init and Catkin build, and you have your Catkin workspace. So you have your Catkin workspace. In our application, we had 4 nodes. So I will go through to show how one node is created, which is the pick and place node. So inside the source folder, I create a Catkin package with the pick and place, which is the name of my package, and the dependencies. And then the folder structure is like this, and you can start to build inside this package now. So as I said before, we want to communicate with the nodes using the ROS messages, and creating ROS messages are very easy. So I define my messages in the message definition file here. So I have, as the request, I have 3 strings here, object ID, and from which surface to which surface I want to move my object from, and then the return response from the operation, whether it's successful or unsuccessful. And then in CMake list file, we can use this generate macro message to generate a macro to generate the messages. And this will be a pre-built process which will generate the source file I need to use in my project, depending on your language, of course. Yeah. So given that, the next thing I will go ahead to show you a little bit of code, how to use ROS to develop your node. So in ROS, node handle is the main thing which will handle your communication with other nodes. So you need to have a node handle in the place where you initialize all your servers and clients to talk with other nodes. So here, for example, I have this pick server, which advertise one service pick and place object, and then my callback to my callback function, which will do the actual work when somebody asks me to do pick and place the object, which comes from UI in this case. And then I have a bunch of other clients and one service to update the camera, etc. So as you can see, it's really easy to implement the communication and your channels to communicate with different nodes using ROS. And then the next thing is I have my nodes and I can communicate with my nodes, and then I can put my code, what the actual work I want to do. The next thing is how can I communicate with my move group and my move group and get the robot functionally to work with. So I'll go to the next slide to do that. So the move group actually provide you with different interfaces to access the functionality from move group, and internally they will handle the messages and responses and everything. So here, as I told you before, I use one move group interface, which is for my robotic arm, and then I want to use the pick functionality from move group. So I create a move with grasp message and tell the grasp pose where I want to grasp my object from, and other variables that are necessary to be set there, like where I'm coming to grasp my object and how far I'm going to grasp it, etc., etc. And then you just need to ask the move group to pick the object, and internally inside the move group, it will do all the collision checking, inverse kinematics, and motion planning for you, depending on the configuration that you put in the Moveit assistant. And the work will be done there actually. And then I have this pick and place node now, and to run this one, I can initialize my Ros environment in my main function and start my pick and place executor. And Ros also provides you with launch files to launch your nodes, which looks like this. And you can also have very complex launch files where you can launch different nodes all together and pass the necessary arguments inside that. Yeah, so this is basically how you can easily build a robotic application using Ros. So I will quickly go ahead and show you what I just did here. So I will load my application, and as you can see here, so my environment is loaded. It's just 2 boxes and 1 object here, and my robot is there. And this all is handled by move group, the whole visualization and everything. And then I can open up my panel, which is my UI, this pick and place UI, and I have it here. And I'm going to simulate my camera. Okay, it updated the object, and I'm going to ask it to pick this one. So it's going to plan everything and go ahead and pick it and do the placement itself. Yeah, and done. And I have the other button as well, which should do it in the other direction. So I did it in the other orientation. I'll go ahead and do the placing. So this is basically just a very, very small example how to use the Moveit. But I can show you how we are using that one in our project. So this is our application where we have all the models loaded and use the Moveit and the Ros to build our robotic application. So this I'm running with the simulator now. So we're gonna press some buttons here of the kitchen stove. And all this planning and everything is done with the capabilities from Moveit. Obviously, we develop our own algorithms when it's necessary, but there are a lot of support from Ros and Moveit to do these kind of operations. So that's kind of it from me. So I just wanted to introduce you guys these tools that are there. And the good thing is you don't need an hardware to try these out. You can use the simulators provided by Moveit itself and go ahead and try them. So yeah, so thank you. That's it from me actually. And I also put some resources that if you wanna go ahead and check this out. Yeah, thank you.
Okay, yeah. Can you hear me? Yeah.
Yep.
Thanks, Chamara.
Yeah,
just
sure.
having a look at. Okay. Well, obviously, Matt, you've actually got a question yourself. I'm happy to read it. Do the 2 arms collaborate or work independently?
They collaborate actually. So for example, if I want to do a steering of the pastime cooking, let's say, so they will collaborate. I will take this one, for example, and steer with the other one, or some other operations where I want to put spices together, or while I'm steering, I want to put spices together. Yeah, so they collaborate actually. Yeah, they do collaborate.
It's pretty cool.
Oh, thanks.
Yeah. So Shanna has a question. This is really interesting. What are the system requirements to run this software? You can see that question now.
systems requirements to run this software. Yeah, so mainly as the we need a powerful PC, obviously, to run our algorithms, and we do all the main algorithms in C and C++ at the moment. So this is one thing. We need the GPU as well to run some algorithms and visualizations as well. And the other thing is to communicate with the actual hardware from the robot. We use a PLC, and the PLC is the safe file system that we use to communicate in with the PLC and run the robot itself from the PLC. So we send the commands there, and we have basically these two systems as in terms of the main hardware requirements in terms of the computers, let's say PCs.
Okay. You can again, yeah, questions there.
Categorize the whole simulation environment or run it on bare metal. You can do that. At the moment, we are still kind of bringing the system together. So at the moment, we run it in our main PC basically, and communicate directly to our PLC. But you can have it as a Docker as well, the whole simulation environment, and try the algorithms as well. We can give it to somebody with the Docker version.